I've specifically used the term biometry because I don't want you to get hung up on the maths involved in doing the analyses. Tomorrow or sometime, I will give you an example of some of the statistics programs that are available to do the analyses. I'm more interested in you understanding what the statistics outputs are telling you about the biological system that you're working with. Okay. So let's not get hung up about the maths. Let's get hung up about what the statistical outputs are telling you about the biological systems that we are working with. So I emphasize the word biometry, bio. Okay? Right. Why do we want to do statistics in a course like this or in a meeting like this? There are basically two reasons. The first is it's the language of communication of science. It enables biologists to read and evaluate journals and the figures that are produced in the journals intelligently and to understand statements like, this cultivar yielded significantly more than that cultivar. What does the term significantly mean? Or a term like yield was significantly correlated with cumulative temperature with an R value of 0.97. What does that actually mean? What is it telling you? So we'll do things like that. There was a significant relationship between pre-flowering minimum temperature and pollen viability. And what is that telling you about the behavior of the system? So those are the kind of things that we want to understand and get from a statistics course. The other thing that's important about statistics and statistical literacy is that you need it for trial planning to make sure that your measurements are correct, that what you are claiming to be true is in fact reasonably true, that the hypothesis that you are testing can be validated, and that you have the correct sampling techniques and things like that. And essentially, if you are challenged about your data, you can defend it in some way. The other thing is, can I justify spending money on what I'm seeing? Is what I'm claiming to see, in fact, is there a chance that I'm correct? Or is it a case of my observations are due to just chance variation? So in other words, was my sampling acceptable? So those are the two main reasons that we apply statistics. So what I'm going to do today is I'm just going to introduce you to a few of the concepts of measuring, sampling, and what the numbers mean. Tomorrow we'll start on what do I do with my data. We'll be looking at trial design from the simple t-test, chi-square, going up to more complex analyses of variance. Then we'll get into correlation and regression analysis, and then we'll do some worked examples where we will then see what our data means and what the statistical outputs are telling us about our data. So that's the basic structure that I will be following. The other point I want to make before I continue is the presentation I have here is fairly complex. There's a lot of information, and an hour is not going to be long enough to cover everything. So I'm going to give you the presentation as it is, but I'm only going to highlight the main points of the presentation today. Okay. So what I want to do is I want to start with a few definitions. The reason we do statistics is because we want to understand the biological systems or the biological populations that we deal with. Okay, and in biology, a population is defined as the individuals of a species that interact with one another to maintain this homogeneous gene pool. But in statistics, we can define the population according to our needs. So for example, I can say this room is a population. I have defined the population. Now, in our field, it might be a cultivar, it might be a field, it might be a province, depends on the size of the population you want to work with. But essentially, what happens is you have a collection of individual units that are under investigation. And that then is the population. So you can define a population. So let's define the population here as people in this room, just for to introduce the concept. Members of a population have certain characteristics. Now, if I look around this room, some of us have snow on our heads. Saki Pretorius has snow on his head. Some of us have nothing on our heads, or very little. Okay. Some of us have dark hair, we have short hair, we have long hair. Right. So each of us has a specific characteristic. And the characteristic that I'm measuring, I call a variable. Right. So let's take the people in this room. The variable I want to measure is the height of the people. Okay. So I have a defined population. I now say I want to measure the height of these people. That's the variable that I want to measure. And then to get an idea, because I can't measure everyone in this room, I might measure a few people. In other words, I take a sample from the population and I will make deductions about the population as a whole from the sample. Okay. So what's very important here is that we define our population, we define our variable, and that we define our sample, and the sample has to be measured correctly. Because if I don't measure length of people in this room correctly, I'm going to get a bias, or I'm going to get an incorrect picture of what's actually going on in the population. Okay. Does that make sense? Yeah. With me? Right. Okay. Right. So those are essentially the things that we measure in statistics. So who says statistics was difficult? Right. So we do it in various ways. But that is what we want to know. What is the characteristics, or what is the population? What does it look like? What is the variable? And what is the variation that occurs? And I take a sample with which I then make the deductions. So it's very simple, right? So if we look at the board there, I might define my population as wheat cultivars. I want to measure the plant length or the plant height. My sample is going to be 100 plants. Now, those 100 plants are going to tell me about the greater wheat population. I then have what we call a sampling unit, and the sampling unit is going to be the plant. So if I was doing it in this room, I would take him, and he'd be my first sampling unit. Okay, so that's very simple. So you're measuring plants in a cultivar trial, and you're making deduction about wheat grown elsewhere in the country, elsewhere in the province, elsewhere in the world, depending on how you want to extrapolate the point. Now, the first very important thing when it comes to sampling is that the representative of the population must be drawn randomly from the population. Now, that's very important because I might decide I'm going to sample this room. And I don't like your face. I'm going to leave you out of it. You know, no, you okay, I'll measure you. Right, what am I doing? Bias, right. So you've got to be very careful about bias. Okay. And bias can be very subtle. You can be drawn towards plants with large grains, for example. The other thing about bias when it comes to sampling, for example, if I harvest my trial by hand, I'm collecting all the grains, and I'm going to tell you that the yield is 2 tons per hectare. But now that field was infected by one of Saki's many pathogens that he produced. The grains are lighter because of loss of density. I go now through with a harvester. The harvester blows out a lot of the grains. Right, and I'm now going to tell you the yield was 1.6 tons. Okay? So what happens when it comes to sampling is that you can very easily pick up bias, okay, depending on how you're measuring your sample, and it can be subtle, and you can pick up bias because you didn't use a proper sampling mechanism. And in this case, I'm talking about random populations, or random sampling, sorry. Now, one of the things that we can use to avoid bias is to use a random number table or a random number generator. So most of your spreadsheets, something like Excel, will have a random number generator. Most of your stats book in the back will have a random number table. So you want to go and collect 100 samples. What you do is you run down the column of, let's say, your random number table. And it will tell you to take plant number 10, 15, 18, whatever. I'll then go down the row and I'd say take plant number 10. Now I might get down there and look at plant number 11 and think it looks a lot better. Okay, that can happen. But the point is the random number table will stop me being biased and ensure that my sampling is correct and random. Okay, so that becomes very important. You want to avoid prejudice. Okay. So I'm going to sample plant number 10, plant number 15, plant number 22. And I'm going to ignore everything else. Okay. What also happens very often is a field might be very big. And I park my car at this end of the field. And it's much easier to sample the plants and dig them up and put them in my car. Then I don't have to carry them. So what I can do to avoid bias as well is to decide to divide the field up into quadrants. We call it stratified random sampling. And then take samples, 5 samples, 5 samples, 5 samples, whatever the case may be. Also in a random fashion. And I will get a representation of the field that I'm dealing with, okay, and avoid bias as well. It just means I've got to carry the plants further to get to my car. But the point is my sampling will be correct and it will be representative of the population that I'm trying to measure. Okay, bias, and I'm hammering that point because we have a lot of issues with random sampling, bias, and these subtle little things that creep in when we are sampling fields. The other thing that we need to be careful of is that our samples are independent. That means that a sample that I measure here must not be linked to something else in the field. Again, this is a form of bias. In other words, if I'm measuring temperature, for example, temperature is not independent of humidity, or humidity is not independent of temperature. Because generally, when it's cooler, humidity is higher. When it's hot, humidity is lower. They are not independent. Okay, and that is another thing that can cause bias or misinterpretation of what is going on in a population.